Hello, in this lecture we'll discuss second order differential equations. In this particular lecture, um, there's quite a bit, there are quite a bit of definitions, quite a few definitions, and so if you'll bear with me, in fact, really the majority of this lecture will be definitions and theorems. So really we're introducing the language of differential equations and some of the terminology. Some of it we referred to in the last set of lectures, and it's more formally defined here in the context of second order differential equations. So first of all, a second order differential equation is written here. You can see it has the second derivative of the function y. It can contain first derivative terms multiplied by a function of x. It can contain zero order terms multiplied by a function of q and q of x, and then it can contain separate functionality of x. As long as there are no terms in y that are squared or otherwise nonlinear, so as long as you have only y and its derivatives, the second order differential equation is called a linear differential equation. Notice that this is independent of what these functions of x are, so the functions of x can certainly be nonlinear functions in x, but it's the terms in y that you're looking at to determine whether or not the equation is linear. So if the equation can be written in this form, it's a linear second order ordinary differential equation. If it cannot be written in this form, then it's referred to as a nonlinear differential equation. So next we turn our attention to this function r of x, which does not multiply any y terms. If this function is equal to 0, then basically the equation reduces to 0 on the right-hand side, and we refer to this as a homogeneous equation. If r of x is not equal to 0, then the equation is called non-homogeneous or inhomogeneous. The functions p and q are called the coefficients of the ordinary differential equation. So here are some examples. Here's an example of a non-homogeneous or an inhomogeneous ordinary differential equation, second order, so we have a second derivative term. And then notice that the y and its derivatives equation is set equal to this e to the minus x cosine of x. This term is what makes the equation non-homogeneous or inhomogeneous. Contrast that with this equation below, where we have y and its derivatives all equal, a function of y and its derivatives all equal to 0. Written in standard form, this would be a homogeneous linear differential equation. So homogeneous because it's equal to 0. It contains no terms in x that don't multiply y or one of its derivatives. So an example of a nonlinear differential equation is given here. You can see we have this y prime squared term. That's the nonlinear term. Nonlinear because it is squared. So that's what drives the equation to be nonlinear. So what is the solution of a differential equation? This is kind of some mathematical terminology, but we'll go ahead and read through it. Basically, y equals some h of x, or function of x, is called a solution of a linear or nonlinear second order differential equation on some open interval I, if h is defined and if you can take its derivative twice and its derivative is defined on that interval. And the interval, by the way, can be minus infinity to infinity, or it can be predefined by the user as an open interval on the real number axis. So what happens is if you get this solution h, you should be able to substitute that solution into the original differential equation, and it will satisfy the differential equation. In other words, the equation becomes an identity. So if you take your solution and you substitute it into the differential equation, you should get an identity. And you do that by basically replacing y by h of x. You would then take the first derivative of y and replace the first derivative of y everywhere in the equation, and the second derivative of y, and replace that as well with the second derivative of h of x. So This is true not just for second order differential equations, this is true for any differential equation. You take your solution, substitute it into your original differential equation. If it works, it gives you an identity, then you know it is a solution. It is not necessarily the solution, but it is a solution. So the difference between talking about the solution and a solution. Uh, Linear differential equations have a very rich solution structure. If we have a homogeneous equation, basically the fundamental principle of this structure is called the superposition or linearity principle. So basically what that means is you can get additional solutions from your given solution by adding them or multiplying them with constants. And so this leads to a fundamental theorem for a homogeneous linear combination of second order. So this particular theorem is for second order homogeneous. So for a homogeneous linear ordinary differential equation, any linear combination of two solutions on an open interval I is itself a solution of that differential equation on that interval I. So in particular, for such an equation, sums and constant multiples of solutions are themselves solutions. Note that this is limited to two solutions because, as a general rule, when you take multiple derivatives, you will generate one potential solution for each order of derivative. So a second order differential equation will generate two independent solutions. Now, if you have an initial value problem, basically what an initial value problem is doing is it's specifying known values of the function and its first derivative at a particular point in time and space or space. So for example, if y is a function of x, as long as you have one value of y that's specified and one value of the first derivative of y that's specified, those are known as initial value or initial conditions. Sometimes in other fields, for example in electromagnetic field theory, these can be referred to as boundary conditions, particularly when you're talking about spatial problems. When you're talking about temporal problems, they're normally referred to as initial value problems. Note that initial does not necessarily have to be at t equals 0. It almost always is, but it doesn't necessarily have to be. We can still solve an initial value problem as long as we have one constant specified at a value of y and one constant specified at the same value of y prime. So why do you need initial values? Well, remember that when we solve an ordinary differential equation, a second order differential equation contains a second derivative of y. So if you think about what the original function was, basically that original function was differentiated twice to get your differential equation. So it contains a second derivative. So when you take a second derivative of a function, any constants in the original functions will differentiate away to 0. And any terms that are linear in x will go to 0 when the second derivative is taken. So what that means is there could conceivably be two constants in your solution that were differentiated away when you took a second derivative. Now, as you integrate, remember that integration always, indefinite integration, always introduces a constant term. So every time you have to integrate, so in a second order differential equation to get the solution, you're effectively integrating twice. So you're going to generate two constants. So the use for these initial conditions is to determine the two arbitrary constants of integration. So here is what is referred to as a general solution. So we have a solution y1 and we have a solution y2 because it's a second order differential equation. So we can get up to two solutions. So we have these two functions that are solutions. And in order to find a general solution, we take each one of these specific solutions and we multiply it by some unknown arbitrary constant and add them together. So this is the superposition or linear combination of the two possible solutions of the ordinary differential equation. Now, we use the initial value and the initial value on this slope to find the value of these constants. So this results in a unique solution. and the unique solution will go through the point x sub 0, k sub 0, and it will have k1 as the slope of the tangent at x sub 0. This is called a particular solution of the ordinary differential equation because it has specified the constants. Once again, remember we're discussing homogeneous differential equations at this point, but the same scenario applies to inhomogeneous equations where we also will generate constants of integration, and initial values can be used to solve for those constants. So essentially what you would do is you would come in to your solution structure, and everywhere you have a value of x, you would substitute x sub 0, and everywhere you have a value of y, you would substitute k sub 0, and you would force the equation to be true. You would then take the first derivative of this equation, and everywhere you have a first derivative term, you would substitute a k1 and force this equation to be true. That will give you two equations and two unknowns and allow you to solve for your two constants. So a more specific definition, a general solution of an ordinary differential equation, and once again this is second order, on an open interval I is a solution in which y1 and y2 are solutions on I, and y1 and y2 are not proportional. C1 and C2 are arbitrary constants. If this is the case, y1 and y2 are called a basis of solutions or a fundamental system, most likely referred to in this class as basis. And then a particular solution is obtained if we assign specific values to C1 and C2. So in addition to that, what do we mean when we say y1 and y2 are not proportional? Here's the definition of proportionality. You probably all know it. It just means that y1 is equal to a constant times y2, or y2 is equal to a constant times y1. K and L are numbers. They can be 0. And so what happens here is these two are essentially the same solution if they're proportional. So once again, y1 and y2 to be a basis set have to be not proportional. So that brings up the concept of linear independence. So we say that y1 and y2 are linearly independent if the following holds. So if we have a constant times y1, a constant times y2, if that's equal to 0 everywhere, then k1 and k2 would have to be 0. Otherwise, if we can find a k1 and a k2 not 0, where this equation is true, then y1 and y2 are linearly dependent upon each other. This is a kind of a fancy way of saying that y1 and y2 can't be proportional. So if you think about it, if y1 is the cosine of x and y2 is 4 times the cosine of x, then we could find a value of k1, in other words negative 4, that would force this equation to be 0. Obviously the cosine of x and 4 times the cosine of x are proportional to one another. So in that case, you could not call those two functions linearly independent because there is a value of k1 and k2 where this equation could be forced to go to 0. So if k1 and k2 are not equal to 0, you could see that y1 and y2 are proportional in this case. If you have linear independence, these functions are not proportional. So linearly independent functions might be something like the cosine of x and the cosine of 2x. Those would be functions where you could not get one from the other by multiplication of a constant. So once again, to just reformulate the definition of a solution basis, a basis of solutions on a second order ordinary differential equation on an open interval I is a pair of linearly independent solutions on I. That concludes most of the important terminology that we'll use when we discuss second order ordinary differential equations, as well as higher order ordinary differential equations. So hopefully this will be helpful to you. All of these definitions are found in your textbook if you need to review that.